Okay, so let's start. Hello, everyone. Welcome to the next quantum computing meetup organized jointly by quantum computing groups from Washington, Toronto, and Warsaw. My name is Pavel, and I will be the moderator today. We have pleasure to host the great speaker, Dr. Emil Żak, who actually is from Poland as well. So we are in different cities, but in the same country now. And he will give a talk, Simulation of Quantum Chemistry, Hamiltonians with Relativistic Effects on Fault-Tolerant Quantum Computers. So before we start, just a few announcements. So first of all, as you can see, this meeting is recorded, so hopefully the video will be later available on our YouTube channel. And we've also agreed with Emil that if you have any questions, please post your questions on our chat, or just write down on the chat. And there will be a break in the middle of the talk, more or less. And at the end, there will be also a Q&A session. So we'll try to ask your questions. And of course, at the end, there can be longer discussion during the Q&A. So then you can also raise your hand and unmute yourself to ask a question. We would also like to announce our next event. So next week, Elliot Miller will tell about deep learning generalization, novel methods for ensuring AI can be trusted. So this will be rather connected to AI than quantum computing, but we know that this topic is also very interesting to some of you. Then in July, Dr. Shanti Dimyat will tell about physics of light-dense matter, quantum and classical effects. Later in July, Martin Muschel will tell us about generative AI and beyond, so another talk related to AI. And then on July 27th, Zeki Seskir will tell us about educating to the culture of quantum technologies, a survey study and concepts for public awareness. And then in August, I will give a talk about optimizing complex processes using AI and quantum computing, so it will be partially based on my PhD thesis defended just a few months ago. And finally, I would like to thank our partners and sponsors for supporting us and helping us make this event happen. All right, so I will stop sharing my slides now. And Emil, first of all, thank you for accepting our invitation. It's our pleasure to host you. And if you are ready, the Zoom is yours and you can start the talk.
Thank you. I appreciate it. Well, hello, everyone. My name is Emil, and I'm a physicist at BEIT. And today I'd like to talk about simulating quantum chemistry Hamiltonians, especially with relativistic effects on fault-tolerant quantum computers. So a few words about BEIT. BEIT was founded in 2017 by three vibrant ex-Googlers, Paulina Mazurek, Wojtek Burkot, and Witold Jarnicki. And we've got offices in the US, Poland, and Canada. And with around 15 employees at the moment, we have submitted around 30 patent applications and received a bit more than $10 million in non-dilutive and private funding. So the grand scheme of actions here for the electronic structure simulations is that we usually take the electronic Hamiltonian, for which we solve the Schrödinger equation. And we get selected energy levels and orbitals, as shown here. So this is the usual way we do it. And based on these, we might try to calculate some derived properties, such as some static pictures of reaction pathways, some catalysts, transition dipole moments, absorption spectra, some thermodynamical properties of molecules or crystals. And based on these solutions, sometimes we also aim at supporting the dynamical properties of matter. So we turn into dynamical calculations. We might think of calculating electron currents, some transport properties, or vibrational dynamics. So it turns out that a significant portion of problems and challenges relevant to industry and academia is related to spin dynamics. Thus, in this talk, I'd like to present an approach that we developed to simulate this electronic structure on quantum computers, but including spin effects. And so for this purpose, we'll be solving not the electronic Schrödinger equation, but the Pauli-Breit relativistic equation. So here's the outline of my talk. As I said, I'd like to say a few words about the Pauli-Breit Hamiltonian first. Then I will probably discuss the use cases. When do we really need such relativistic effects to be included? And next, I'm going to do a quick survey of quantum algorithms for Hamiltonian simulation. After that, I think it will be a good point to show you a few tensor network-based approximations to this Pauli-Breit Hamiltonian. And I'm going to move to showing how some old techniques or some already published techniques can be used to readily simulate these Pauli-Breit Hamiltonians. Especially I'll focus on the Majorana representation. And at the very end, I'll drop a few circuits which are new, and they aim at reducing the complexity of simulating this Pauli-Breit Hamiltonian. And we end up with some quantum resource estimation for these techniques. So going to the Pauli-Breit Hamiltonian, this Hamiltonian is a perderivative approximation to the Dirac equation, and it consists of 6 main terms. There's this pure electronic Hamiltonian, the so-called Darwin terms, D1 and D2, spin orbit terms, and spin-spin. So to set the stage, I'm going to consider a system of M nuclei and, let's say, eta electrons. And capital R denotes the position of the nuclei, and lowercase r are the coordinates for the electrons. P is the momentum operator for the electron. So this is the standard Coulomb electronic Hamiltonian that quantum chemistry is based on. But the Pauli-Breit interaction Hamiltonian contains extra terms. They are called the 1 and 2 body Darwin terms. This is how they look. There's no need to dive into too many details about those. There's also this part called the spin orbit interaction, and it also contains this 1 body part and the 2 body part. And here in this equation, this L is the electronic angular momentum as we anticipate from the orbit. And there's also S, which is the electron spin operator. So maybe against some common knowledge, the spin orbit interaction is also a 2-body interaction. And finally, we have this spin-spin interaction term where spins are coupled. Nonetheless, this term is usually order of magnitude smaller because of this inverse 5th power dependence on the distance of the electrons. So this is how the Pauli-Breit Hamiltonian looks like in a bit of detail. And now I'd like to switch to a couple of slides with motivation, like why do we care about this Hamiltonian? So first, open shell molecules, in order for them to be treated adequately, we must include the so-called spin-orbit interaction in order to get accurate predictions. Let's say if we want to simulate spectra, optical spectra of molecules, so-called rho vibronic spectra of small molecules, we must calculate on the way the so-called spin-orbit coupling curves. So here we can see these curves and some spectrum for yttrium oxide. This is just an example. And here in the left bottom corner, there are listed energy levels of iron oxide, which we can see there are states with multiple spin multiplicities. So in order to do it accurately, we have to include somehow these relativistic or Pauli-Breit originated effects. And ideally, we'd like to use quantum computers to not resort to models and to approximations, but do it like from first principles. Another example is the internal conversion process. So during absorption of photons by matter, one might expect fluorescence happening and some internal conversion. So we excite our system from a singlet state to a singlet state. And this electronic Hamiltonian that we had before, it doesn't describe some of the relevant processes like the inter-system crossing. And this crossing is due to interaction of the triplet states with the singlet states, or states with different multiplicity. And this is steered by the spin-orbit interaction, in fact. So, there are competing processes in such relaxation scheme where the intersystem crossing leading to phosphorescence competes sometimes with the fluorescence. And this mechanism is quite relevant to spectroscopy, photochemistry, organic chemistry, photomaterial design, and much of biochemistry as well. Against also common knowledge, spin-orbit coupling is relevant not only for heavy atoms. It's mostly important in heavy atoms when you have a heavy atom. But sometimes when the atoms are moderately heavy or even light, the two-body part of the spin-orbit interaction may still become significant. So we're not letting it go easily, because we would like to include all the effects that contribute to the overall accuracy. And we would like to use this quantum computing to use adequately accurate models. And these terms have been usually dropped due to computational complexity on classical computers. So there are certain instances where these highly detailed and accurate terms will be relevant. I'm not saying all applications. Another example is in photomaterials design. So the so-called spin vibronic coupling is key mechanism in steering this electron-hole recombination process. So modeling this accurately might help us design new materials. Another example, simulating NV centers, also important for the design of spin qubits. Spintronics, they all at some point, at some stage, contain parts of the relativistic Hamiltonian. Also, a good part of biochemistry and catalysis leverages on this heavy atom effect, including the spin-orbit interactions. So I'm dropping here a couple headlines from peer-reviewed journals, usually high profile. And so, for example, here in the top, you can see a heme molecule where there's it binds oxygen, and this oxygen binding molecule process is spin forbidden. Plus, the spin orbit coupling must be responsible for one of these fundamental processes to life. Therefore, I believe that it should be understood at adequately high accuracy. So we would like to include all relevant quantum effects, and there are a couple of such effects involving spin and vibrations as well. Another example, reactive scattering or bimolecular reactions, they can be steered with, or they are believed to be steered with the spin-orbit coupling. So these branching ratios of the reaction products depend on how strong this spin-orbit coupling is. So this way, we might think of designing better materials if we had this predictive power of quantum computers. A few more headlines. There have been reports in the literature of enzymatic reactions that are spin forbidden. Hence, in order to understand this process, we must include spin-orbit coupling. Usually it's done at a low level of accuracy, but it would be great to have. Maybe some new effects will pop up when we have higher accuracy available. Another example, and almost final one, is the photodynamic therapy. So in photodynamic therapy, there are photosynthesizers, and when they interact with light through the mechanism of intersystem crossing, which is traced back to the spin-orbit coupling, they produce reactive oxygen species, which then act as active agents, killing the cancer cells. So I would say last but not least, there's an example where we would like to mimic nature by designing catalysts that convert CO2 into carbon monoxide or some further useful compounds. And this is called artificial photosynthesis. So we would like to design materials or catalysts that enable this process to happen effectively. There's a huge potential in this industrially. And one of the key processes here is steered again by the spin-orbit interaction and other relativistic effects because of the heavy atoms involved. You might look up this report by very fresh one by Los Alamos National Laboratory. So as you can see, the spin-orbit coupling and other relativistic effects are relevant to the small and to the large. So starting from small molecules, open shell molecules, and high accuracy calculation for those through this internal conversion dynamics to oxygen attachment in heme of hemoglobin, and finishing at very complex enzyme processes. I'm not here to convince you that the spin-orbit interactions are ubiquitous and significant. That's important across many fields, but nonetheless, I've dropped a couple of articles and headlines that point to, I believe they point to necessity of accurate modeling of these electron spin interactions and dynamics at various sizes, various scales. So surely there will be an area where high accuracy first principles, Pauli-Breit Hamiltonian simulation will benefit all of us. So switching to a bit of physics now. I'd like to show how the Pauli-Breit Hamiltonian that we already seen can be second quantized. So first, we choose an orthonormal basis of spin orbitals, where this ket, in this ket, we've got P, which denotes the spatial orbitals, and sigma is the spin variable. So this is a standard basis, sometimes represented in this position spin representation shown here. This is standard, And then, having this basis, we pick the ladder operators, the fermionic ladder operators that kind of form the Fermi-Dirac statistics. So they anti-commute. So I chose a technique called the unitary spin-dependent unitary group approach, where we represent the Pauli-Breit Hamiltonian with the generators of the U to N Lie group, where N, I repeat, is the number of orbitals that we have. So in this framework, you might express the one-body operators that appeared in the first quantized Pauli-Breit Hamiltonian as follows: just a linear combination of these generators with matrix elements. Similarly, the two-body operators can be expressed with these generators here. So, as you know already, there are operators in the Pauli-Breit Hamiltonian that explicitly depend on spin, and some don't. So for those that don't depend on spin, for instance, the electronic Hamiltonian, we might simplify this picture, and instead of expressing the two-body electronic Hamiltonian with these U of 2n generators of the Lie group, it is possible to reduce this representation to the U of n generators by tracing out the spin variable. So this is one of the familiar, probably familiar forms for the electronic Hamiltonian, where we've got these creation annihilation operators, but hidden here. So this two-body part is also sometimes called this two-body spin orbital replacement operator, but it's nothing else that a combination of annihilation and creation operators, fermionic ones. All right, so first let's turn our attention to the one-body operators, okay, that depend on spin. We'll produce something called the triplet excitation operators, denoted here with T. And they depend on the orbital indices. They are one-body operators, and they've got these components here, mu, that are Cartesian. So it's x, y, and z. And they are created as a linear combination of these U of 2n Lie group generators with coefficients being elements of the Pauli matrices. So this is a standard technique in quantum chemistry, where you produce these symmetry adapted SU2 operators in the U to N group. They are also called rank 1 tensor operators over the SU2 spin space, and they satisfy this nice commutation relation with the spin operator. Hence, they might be called vector operators if you want. So with these triplet operators, it is possible to express the one-body term in the Hamiltonian in a quite compact way. And here this H is in fact a vector of different operators that enter our one-body Hamiltonian, our Pauli-Breit Hamiltonian. So there's the kinetic energy of the electrons, the electron-nuclei interaction, and the one-body Darwin term, and some orbital terms stemming from different Darwin and spin orbit terms. So the whole spin information is moved to these triplet operators. And again, P is just a vector of these Pauli matrices, but it's extended with where the zeroth component is identity. So it's a particularly compact form. And we might try to expand it, so not to operate within these triplet operators, but just leave it in an expanded form. So again, the one-body operator would be a sum over all Cartesian components or four vector components, spin variable sigma rho, and orbital indices p, q. And that would be these Pauli matrices, these matrix elements of these spin-independent Hamiltonians, as we can see them here in the bottom, and these excitation operators. So one observation here is that we moved the spin dependence away from the matrix elements of the Hamiltonian into so-called analytic Pauli matrices that we usually know how to handle on quantum computers. So we're going to make use of that in a moment. But please take a moment pondering on this, and that the spin interactions, in fact, and if you look deeper, they don't really contribute that much to this curse of dimensionality in quantum paradigm. They span these two s+1 representations. They don't do this exponential scaling. They just can be kind of left out, and they give a multiplicative factor, not much. Nevertheless, we need to know how to handle them. And one extra observation here is that what we can see here, in fact, is a sum of products of some SU2 or U2 operators and UN operators. And so we expressed our Hamiltonian with generators of a product of UN and U2 subgroup of the U to N. And this is sometimes called the spin orbit subgroup. So I think this is a non-trivial transition here. So the two-body Hamiltonian. So this was previously just one-body Hamiltonian, which is straightforward. The two-body Hamiltonian is a bit more involving if you express this Hamiltonian with these excitation operators and Pauli matrices. It gets a bit messy. There's also an add-on to the one-body Hamiltonian, which is equally messy, but we don't bother about this at this moment. So instead of writing it down this way, we might write it down in a very compact form by, again, utilizing these triplet operators. So you remember these triplet operators are these SU2 symmetry-adapted operators. So this is sort of a quadratic form in these triplet operators, or can be viewed as also as a tensor contraction of rank 4 tensor, or even rank 6 here. So this G matrix and C matrix look like this. So you can see all the components of the two-body operators that are witnessed in the Pauli-Breit Hamiltonian. So there is an electron-electron interaction, the two-body Darwin term, the contact interaction, and some orbital terms here, and spin-spin interaction in the middle. And there's a sort of trivial C matrix. So to give you a little bit of intuition of what this is all about, what the spin-orbit coupling does to the excitation scheme that probably we know from quantum chemistry, is that if you have a set of orbitals, let's say P and Q, and you've got an electron spin up, which is alpha here, and you want to excite it to another orbital. So you go from Q to P. the spin-orbit interaction weighs the branching ratio between the spin flip and no spin flip event. And so this term HSO plus is exactly this special spherical tensor form for the spin orbit interaction, but it's just a coefficient which tells you how probable it is that a spin flip occurs, and how is it coupled to this specific PQ transition. So this orbital transition, so it sort of couples the orbital motion, as we see, to the spin motion or spin excitation. All right, so to wrap up all this, we've expressed the Pauli-Breit Hamiltonian in second quantization, and it takes a particularly simple and elegant form where there are these one-body terms, which we've seen they look like that, and there are these triplet excitation operators, and the two-body terms that are a quadratic function of the triplet excitation operators. Obviously, the underlying mathematics is messy, right? So if you unfold them, they're quite long equations. So now, having said a few words about this Pauli-Breit Hamiltonian, I'd like to switch to a quick overview of quantum algorithms for calculating eigenvalues of Hamiltonians. And one of them is quantum phase estimation. So in quantum phase estimation, we've got a register of n qubits. So it's sometimes called the estimation register here at the top, this guy here. And this estimation register is initiated in an equal superposition by Hadamard gates. And later on, we apply controlled unitary transformations on all possible combinations of these states, essentially. And we act on so-called system register. The system register is initialized with state psi. And the state psi can always be decomposed into a linear combination of eigenstates of our Hamiltonian. So the end goal is to get an estimate for the eigenvalue of the Hamiltonian. Every state can be projected onto a linear combination of eigenstates of Hamiltonian. And so we carry on with several controlled unitaries. I'm going to tell you what these unitaries are in a moment. And we wrap up this sandwich with inverse quantum Fourier transform and measure all the register qubits, these estimation qubits. So the measured bit string gives an estimate for the jth eigenstate energy. And so in order to retrieve the eigenvalue of the original Hamiltonian, we must classically multiply this number that we get by the norm of the Hamiltonian. This is by construction of this algorithm. And so this evolution operator that enters these unitaries is an exponent of the Hamiltonian. And there's, because it's a projective representation, the power of this operator enters here in the argument of the exponent, and it's divided by the norm of it. So you might summarize this quantum phase estimation algorithm with such a statement that with probability Cj modulus square, where Cj is the coefficient standing by the lambda jth eigenstate of the Hamiltonian, quantum phase estimation returns an approximation to the eigenvalue theta j of h over lambda. So this is what we get here. And this is our n-bit representation of this theta. Hence, our precision is to the power of -n. So this is what we get. And the respective system register is projected onto the lambda jth eigenstate of the Hamiltonian. So this is how it operates. So now we know how it operates by and large, but what's even more interesting is what's the cost of this algorithm. And as you can see by inspecting the picture here, the cost of QPE consists of the cost of quantum Fourier transform, which is irrelevant here, I would say. It's fixed to some point, to some degree, or doesn't scale badly. There's a cost of controlled unitaries, these guys here, and the cost of state preparation, so how to prepare a state with high overlap with our desired state. So based on this, and even minding what's been shown before, that we get an eigenvalue of h over lambda after this precision, we might need to perform lambda over epsilon, where epsilon is exactly this to the power -n repetitions of the circuit U here, in order to compute this eigenvalue of the true Hamiltonian, not the divided by norm, at this precision epsilon. So if we need to do this controlled unitary this many times, it must enter the cost as such. So here in this bit, you might see just a different representation of this cost here. It's to the power of n, so it's 1 over epsilon. Lambda is the norm of the Hamiltonian, and we've got something called the cost of the block encoding of the Hamiltonian in this unitary here. And there's also a factor related to the statistics, so how frequently we get this state. So it's 1 over the overlap of our state, desired state, with the current state, the input state. So the variable cost here is usually the cost of block encoding the Hamiltonian. So how to represent this unitary, this highest power essentially of U on a quantum computer, and it points to this first to the procedure of block encoding, but then you somehow have to approximate this exponent, which is done in a number of ways. You might have heard about Trotter approximation or qubitization or quantum signal processing. So I will focus from here on in on the block encoding circuit, because this is the key part here, and a bit on the norm of the Hamiltonian, because this is something that we might control. So after these two slides, I'll probably do a little break. So if you feel like asking any questions, just stay tuned.
Okay.
I'll be great. So in about a few minutes, I'll be happy to answer what's been popping to your head so far. So block encoding of the Hamiltonian. Let's say we agree that this is a key player or key contribution in the overall cost, a key component. And I'm going to show you how one can block encode a Hamiltonian that's been transformed into a specific form. Because Hamiltonian is a Hermitian operator, but this is by no means a unitary operator, and only unitary operators can be implemented on a quantum computer as quantum circuits directly. So by expanding our Hamiltonian as a linear combination of unitaries, like shown here, so AJ is a number, just coefficient, and UJ is some unitary operator. It's called linear combination of unitaries. If you can do it, then the block encoding of this Hamiltonian divided by the norm of it into a unitary circuit can be done with these three following operations. State preparation, UP, selection of unitaries, US, and uncomputation of this state preparation. So in a picture-wise approach, you might think of embedding your Hamiltonian in the top left corner of the bigger unitary matrix, which is fed into the quantum computer. And if you project out onto this space of H, which means measuring some zeros of some ancillas, you will effectively act with this Hamiltonian on your qubits down here. So this prepare, so UP, the preparation unitary, basically does a simple thing. It prepares, as the name says, a linear combination of states with coefficients being square roots of these coefficients here. And there are some index states. And on the other hand, this select operation selects or projects out this one-dimensional subspaces of these index registers and acts with the UJ operators, so with these unitaries. It's pretty simple framework. And the circuit that we might draw for this type of approach can look like this. So the block encoding of the Hamiltonian, i.e. this big unitary matrix, is consists of these two multi-wires, let's say. The first multi-wire or register has a logarithmic size with n, where n is the number of terms. And we prepare our states on log n qubits. Then we do controlled unitary, so this selection operation that we've seen before. And then we uncompute and measure. Given we measured all zeros, we project it effectively onto this space. So as you might infer from inspecting this image, the overall cost of block encoding would be a cost of state preparation, CUP, cost of selection of unitaries, and the cost of uncomputation. As simple as it looks. Okay, I think I would stop here for a moment, sip a glass of water, and possibly address some of the questions or doubts about that.
Okay, thank you. Thanks, Emil. Yes, we have a few questions here on the chat. So let's start from the question what was it? From Itamar about the spin orbit, just a basic explanation. Yeah, if you can explain it briefly.
Right, what is spin orbit as such? Well, let's say in an atom, we've got electrons, and every electron has a spin 1/2, right? It's an intrinsic angular momentum. And this intrinsic angular momentum, as a form of angular momentum, might interact with the orbital motion of the electron around an atom. So there are states which have a non-zero angular momentum. You might have heard about the p orbitals or d orbitals. And these states, given that we allow for this interaction through this Hamiltonian, these states might effectively split into two due to this interaction. And physically, it's just that the motion of the orbital motion of the electron around the nucleus is sort of coupled to this small gyroscope. So the spin, it's just two gyroscopes. So effectively, neither angular momentum of the electron, the orbital one, nor the spin are good quantum numbers. You have to add them in a vector sense. So I'm trying to layer out different let's say, levels of the answer, from very picturesque to maybe a bit higher level. Yeah, so this is what spin-orbit interaction is, essentially. In terms of operators, it's just a product of the angular momentum, the orbital angular momentum operator, which is a vector, and spin operator, which is also a vector. So sometimes it's a scalar product of these two vectors. So X, Y, and Z components.
Can we distinguish between weak and strong coupling?
Do we distinguish between weak and strong coupling? I presume it's spin-orbit coupling. Right, so there are these historical frameworks of so-called JJ coupling and Russell-Sanders approximations, and here we don't care about this. So we don't care about how I believe we shouldn't care about how the spin vectors are added. In which order is it that we first add spins together and angular momentums together, or do we treat angular momentum and spin jointly and add them up? So I don't think at this point we care. I think it's lower level. So we don't even recognize this type of approximation. We just assign spin to a particle like electron and assign. So it's first principles, like totally first principles here.
Okay, thank you.
Yeah, no worries.
Good. Thanks. There's another question from Cheng. What does it exactly mean by PB Hamiltonian can be expressed in subgroup of U to N?
Oh, that's a very detailed and nicely spotted question. Well, the way I see it is I've got a Hamiltonian, an operator, which is Hermitian, and it gives rise to a Lie group or some Lie representation, like exponent of this operator. So normally this operator acts in the space of 2n spin orbitals. That's what we said, that we've got n spatial orbitals and we've got spin up, spin down. And instead of living in this space of 2n orbitals and taking the exponent if you want to calculate the evolution operator directly, and you would live in this 2n by 2n space. It's not this size, but we live in this. We say we live in this space. Then, instead of doing so, you might detach this electron spin analytically and say, yeah, we know that electron spin is fully described by SU2 group or U2 group. So this U2 corresponds to the Pauli matrices here. And what's left is an operator that, does it depend? I think it might be a little typo here, if I'm right. There might be a little typo, which, yeah, I believe so, where this shouldn't depend on spin. No, it does depend on spin. It does depend on spin, of course. So if you put these two guys together, it's basically a guy that lives in the U2 group or like operates on spin variables, the T operator. And there is another operator that lives in the orbital space. So the U of N Lie group generates this, like as if we forgot about spin or like treated half of the spin states. And this is just a linear combination of such products. So each operator has certain symmetry, and this symmetry dictates this label here. So instead of having a U to N, we just expand this operator as a sum of products of operators that transform as UN. and u to n. This is, I think, the best explanation I can give, which might be not the most accurate one, but I hope it sort of answers your question.
Mm-hmm. Okay. So there's another question from Cheng, but first I will ask the question from Kevin. How can we talk about entanglement in these systems? Orbital entanglement, electron entanglement, entanglement entropy?
Okay, that is a very wide question. I don't fully understand every bit of it.
Okay,
so let's
I think
focus.
that, yes, I think it was asked during the slide about quantum phase estimation or just before.
All right, all right.
But Kevin, maybe you can unmute yourself and try to clarify.
Yeah, can you hear me?
Yes.
I mean, before the quantum phase estimation, when you actually present the energy levels.
Before, okay.
Yeah.
Let's go before.
Right there.
Right. Yeah, I believe they are. There's entanglement there. So you might think, right. So I don't know if you recall, there's the simplest model, a helium atom. And the helium atom, the first excited state might be singlet or triplet. And the singlet one, it's 2 electrons, right? There are 2 electrons, and these 2 electrons might be either up and down, and they might be existing in 2 configurations, that there is up, down, down, up. And this configuration might be put into a superposition, plus or minus. So it turns out, and we also might have some other excitations, like maybe some up and the other is up somehow. So there are linear combinations of these configurations, and some of them correspond to the so-called triplet state, and one of those, so the sum of up, down, down, up, correspond to the singlet state. And if you have a linear combination of something that's up and down, down and up, that might be called an entangled state, or it's isomorphic with the bell pair. So this is the low-level explanation, that there are such, and spin orbit coupling exactly couples these linear combinations. So the triplet and the singlet. It mixes them or adds, puts them into a superposition with some coefficients. So it might introduce some or change entanglement if we see it from this perspective. But even here, yeah, I could. It's just a cartoon. It's just a cartoon, but you might think of a spin orbital here in a tensor product with this guy here, and this is before, and now there's after. So if you could sort of produce a coherent superposition of these, you would have an orbital with spin up in a superposition with orbital p with spin down. Surely there is some entanglement there, but I can't comment any deeper without any further specifications of what you're up for.
Perfect, thank you.
I'd like to talk more about this at some point if you wish. We would have to look at the explicit expansions, but surely there is entanglement there.
Thank you. There is another question from Cheng. How to obtain the expression of O lambda over epsilon repetitions?
Yes. Yes. So first of all, assume that we say we want to have our theta eigenvalue, so what comes out of quantum phase estimation, to be accurate down to n digits. And these n digits mean it's binary fraction here. So it means that our accuracy, or basically precision here, is to the power of negative n. Or like the bit that stays right here is already a bit that we don't know, and hence this is the limit of our precision. So the number of these thetas here correspond to the number of these u's here, right? So there are u to the power of 0, u to the power of 1, u to the power of n minus 1, where n minus 1 is exactly the number of digits. So this set tells us in order to get this number up to n digits, you need to do n repetitions of controlled unitary. But still, this is happening with ever-growing power. So it's not fully accurate to say repetitions, but it's number of executions. And then I assign just epsilon, saying epsilon is, I should have written it, epsilon is to the power negative n. So epsilon equals precision. Hence, this is the number of repetitions, and lambda is here because I need to, in order to get the eigenvalue of h, I need to multiply this theta by lambda. So I have to do it again, lambda times more, like lambda more times here, in order to conform to this precision. Because I'm boasting this number. If I get theta, and I want to get the eigenvalue of the Hamiltonian up to precision to the minus n, and I know I get this number, I need to multiply classically this theta by lambda, and this sort of spoils the precision. So I think this is a rough explanation why this is the number of repetitions. So-called Heisenberg limit. It's one of the epsilon dependence is the best you can get from a quantum algorithm that we know.
Okay, there's another question from Anurag this time. How does the second quantized method help the calculation faster for these many body problems, or does it give a more accurate result even in quantum computing?
Okay, if it's faster, so it's at a very low level, it's an equivalent picture to first quantized picture. But there are benefits from one over the other, and I'm not claiming that the second quantized form of the Pauli-Breit Hamiltonian will be better than the first quantized form to put on a quantum computer. You might have a look at the work of Rand Babush from the Google Quantum AI group, who him and his colleagues invented a wonderful procedure for the first quantization, which is shown to be just dominating over the second quantized picture. But here, the second quantized picture delivers, let's say, particularly simple forms of the Hamiltonian and detaches the spin in an elegant way, like there are polymatrices and some. So this is probably one reason, and the other reason is just interpretation. It's just more elegant, it's simpler, that you work with excitation operators and you have your orbitals discrete, labeled, or generated with powers of these ladder operators. So it might be a matter of choice if you pick second quantized or first quantized picture. But we'll see some benefits of the second quantized picture in a moment for quantum computers, I believe. So stay tuned.
Okay, and the last question for now. What is the biggest size of a system you have successfully applied this method?
So to be honest, I haven't applied this method computationally, of course. So you might use quantum chemistry software to get the eigenvalues of the Pauli-Breit Hamiltonian for big molecules sometimes, given some approximations there. So this is classical computing. I haven't done very much of this. Don't have much experience in doing those, but on a quantum computer, zero, because we don't have a running quantum computer. So what we've done so far is just sort of resource estimation. How many gates would we need for a system of a given size? So this is the stage of research, basically. And nobody has ever applied any fault-tolerant quantum algorithm beyond very few bits and qubits. So we're still waiting for the hardware to catch up. Mm-hmm.
Okay, thank you. I don't see more questions now, so I think we can proceed.
All right, thanks. Very detailed questions. Thanks, guys, for that. So we stopped at the block encoding of the Hamiltonian. And now I'd like to move to a more research part rather than educational part. Well, I'd like to simulate the Pauli-Breit Hamiltonian. And what's available so far on the market, let's say, are some wonderful methods that can simulate the electronic Hamiltonian. So spin-free, doesn't depend explicitly on spin. And I'm listing two of them here. There's one approach by Vera von Berg, an excellent paper on double factorization of the electronic Hamiltonian, which I admire a lot, and a paper from Lee and from Ryan Babush's group on tensor hypercontraction. So I'm pointing your attention to those papers. So I'm going to use a method of double factorization or a modification of it to try to embed this Pauli-Breit Hamiltonian in a quantum computer. A few words about the double factorization. So let's pick a second quantized form here on the left of the two-body electronic Hamiltonian, spin-free. Let's forget about spins for now. This is a sum over 4 indices with these creation annihilation operators. This is the standard way to do it. And might be schematically written as 2 entries, PQ, PQ, RS, and something in the middle. So you might do a sort of an SVD-like or a tensor rank reduction procedure on this and approximate this rank 4 tensor with a sum of squares of sum of rank 1 tensors. And schematically, it's shown that you have just some M and line in the middle, so you split into 2. And you might go further with that. So there's rank 2, why not to go to rank 1? And you might do it. So here in the middle, we've just decomposed this rank 2 Hamiltonian or matrix elements of the Hamiltonian into rank 1 tensors, which are in fact vectors. So there's an eigenvalue or singular value, and there are vectors here. And basically it might be written schematically that you've got P, Q, and now we've got this guy here just split into 2. And there's L in the middle, so this is this L. And you've got these vectors, so there's vectors. And you just reflect it saying there's a square of this, so like you apply it twice. This is just a general, very rough intuition how it works. So instead of having n to the power of 4 terms, right? So each index here runs n to the power of, from 1 to n. So you should have n to the power of 4 terms. You might use symmetries and say, yeah, there are 8 symmetries here, because the orbitals might be exchanged. The orbitals in the two electron integrals might be exchanged. So it's going to be n to the power of 4/8. But this is quite nasty scaling, so you would like to do better, and this is what this factorization offers you. It just truncates some of the dimensions, and you might boil it down to something like roughly n square number of terms. So you reduce the number of terms by throwing out, in fact, the low singular values in the SVD decomposition of these matrices, of these matrices, because there are always such values. So having described what this double factorization is in a nutshell, we must introduce something that's called the Majorana representation. And the Majorana representation is defined by linear combinations of annihilation and creation operators. So here A sub p sigma is just an annihilation operator of orbital p and spin sigma. And again, there are two such operators. So you might take a plus combination of those and minus combination of those with some phase. And you get two new operators, like gamma p sigma, the 0 type, so the first one, gamma p sigma, the first type. And the nice property of these operators is that they also anti-commute. And they are Hermitian, which delivers some very favorable properties that we're going to use. So, for example, if we chose the one-body spin-orbit Hamiltonian, and we started from this second quantized form as before, it is possible to switch to the Majorana representation and express these spin-orbit one-body terms, the Cartesian components, with these Majorana operators. And they take a particularly elegant form, that there are Pauli matrices in the middle for all these components. There's also, for the Y component, there's a residue, which is sort of dirty, but in certain cases, I believe, for certain model systems, they are. It is 0, or even if it's not 0, it's not a big issue. So the Majorana representation can be applied also to spin-dependent operators. It has been applied before by Berg et al. To the electronic Hamiltonian, but there's no reason to not apply it to other operators. So now coming back, a general operator. Let's take a one-body general operator. So this was just the previous slide was just the spin orbit. Now let's take all inside, and the matrix element of this one-body operator, which has p sigma q rho. Yeah, it might be decomposed along the lines of the factorization that we just showed as a sum of some numbers. So like S eigenvalues, some vector labeled with L, and there are these elements. So this vector can be viewed as, let's say, a row vector, or maybe here it should be column. Yeah, this guy should be column vector, and then the transpose is the row vector. So you produce a matrix, a rank 1 matrix. So in fact, every component in this sum is a rank 1 matrix weighted by the eigenvalues Fl, and you reconstruct the matrix element H1 p sigma q rho. And this is how this factorization basically works. So it transforms this original Hamiltonian, which is given first in the ladder operators and later in the Majorana representation into a sum of the following unitaries. So if we take the one-body Hamiltonian and switch to Majorana representation and do this decomposition of matrix elements, you might express your Hamiltonian as a linear combination of unitaries. And this is what we want. We want for block encoding. And these guys here, lambda L0 and lambda L1, are defined here. And they are just linear combinations of Majorana representations, of Majorana operators, gamma, p, sigma, x, where x is just 0 or 1. And this is the second index. So by doing this decomposition, putting this into a Hamiltonian and folding these sums into such a new symbol, what we discover, I mean, this is what Vera von Berg discovered essentially, that these operators in a product are a unitary operator. Hence, they can be decomposed nicely into a product of unitaries. So this sum is folded into a product of three things. And this is the key here, actually. Now we are ready with this form to block encode it. And the two-body Hamiltonian can be done the same way. So we've got the two-body Hamiltonian, which is a sum over some index R. As before, I think before it was M. I can show you. Before it was M, now it's R. But that's life. So this sum over R now contains T2. Stay with me. T2 is the second Chebyshev polynomial of the first kind. Or in simple words, it's just a square. As you can see, this is 2 square minus 1. It's just a square of a one-body Hamiltonian. And it's divided by the norm. So this is nothing else than just a different way of writing this, or writing this basically, but with spins included. So again, this is a unitary operator, T2. So we expressed the two-body Hamiltonian as a linear combination of unitaries. And the coefficients here now, they are norms of these one-body Hamiltonians. Before we had the eigenvalues or singular values. So this one-body Hamiltonian is expressed here. So by doing this factorization twice, we arrive at a nicer form, and we might truncate these sums, not at n or n square here at n square, but something smaller, like half of it, or even less. It might be a bit heavy, I know, but stay with me. So having produced a Hamiltonian that's one body and two body in a proper form, we want to block encode it. But how do we do it without even talking about qubits? So we have to map them onto qubits. So I introduce here two schemes for mapping between spin orbitals and qubits. One, which we'll call spin major, treats spin as the older index. So the first index in these cats, as you might remember from a distant slide, is the orbital index. And the second index is the spin index. So if it's alpha, let's say it's spin up. If it's beta, spin down. So now spin changes last. And it's called spin major. It's major. The other option is to have the orbital major encoding, where we order our bases such that the spin changes faster than the orbital index. Both are okay. And we have to do a sort of mapping between orbitals and qubits. So one way is to do the Jordan-Wigner mapping, which maps this annihilation operator in second quantization form, so AP sigma, which generates the orbital or annihilates the orbital p sub p sigma, and this Jordan-Wigner mapping is nothing else but a product of Z Pauli Z operators after this index, and there is sigma plus at the index, and identities elsewhere. And this is for spin major mapping. Its form depends on mapping. For orbital major, this place where the sigma plus is located is different. So there are some advantages of one over the other, and I'll show you one in a second. So ultimately, we would like to express our Majorana operators as Pauli operators. So we take a general product of Majorana operators, which appear in these Hamiltonians that we just talked about. This is the atom for our Hamiltonian. And they've got these three indices, P, sigma, and X. Where X, you remember, it denotes the type of the Majorana operator, 0, 1. And they basically boil down to a phase times identities, some Clifford operation at position P, where P is here, and a collection or a string of Z vectors, where these brackets denote the range where the Z acts. So it's a length of this Pauli string. It's closed. And it's closed with another Clifford operation and nothing else there. So, and these Clifford operations, I've listed them here. They are just X or I, depending on the value or on the type, on the case, let's say. And so there's an advantage of using one encoding over the other, some modest advantage in some cases, maybe not in fault-tolerant too much, maybe in NISC. And this advantage, it appears here. So the length of the Z can be made quite small, or way smaller for the orbital major mapping than for the spin major mapping. So the so-called Pauli-Breit, so the number of non-identity operators in this string, might be reduced for the orbital major. And I've calculated this difference between these Pauli-Breits in these strings for spin major and orbital major. And it turns out that if you have different spins, so sigma is different than rho, this is equal to 1 then, let's say, then this difference is big. And if the orbital indices are close to each other, or 0, then still this difference is big, which means that the spin major encoding brings a lot of Pauli-Breit. These strings, these Zs here are long. And this is more physically motivated, like if you look at the structure of the spin-orbit matrices. But it's not a big deal. It's just minor observation, in my opinion. Okay, so this is a digression about mapping to qubits. Now we have to do the block encoding, because we've addressed our problem in qubits. We've mapped it onto qubits, so we're allowed now to talk about wires and things like that. So let's recall and start simple. Let's block encode our one-body Pauli-Breit Hamiltonian, which is a linear combination of these products of these Majorana folded operators. We might write them even simpler, that this gamma 0, gamma 1 is just gamma L. And here we have the block encoding circuit. There's log to n qubits to encode the coefficients, these square roots of f. Yeah, here this prepare unitary prepares a square root of each coefficient in a superposition. There's also a select unitary, which selects this gamma L's, and on computation here. And this gamma L, of course, acts on 2n qubits. So you might also write this select part as explicitly as a linear combination of some projections onto different L index states and these gamma L's. And if you look inside gamma, you have to look inside these. And you might recall that these were unitaries and they were decomposable into something simple. So exactly this select operator now is decomposable into smaller select operators, let's say, select WL, something really simple, single qubit, and the same operation on compute. Okay, so let's have a look at these, at this selection unitary for gamma L. Gamma L, as I said, it's going to be something pretty simple. So it is equal to, yeah, I need to jump between these slides. Gamma is equal to this product of WGW. And this W is essentially this product of these two unitary matrices as described here. So these unitary matrices, they fold these Majorana operators into a vector. And this can be only done because Majorana operators anti-commute their Hermitian. And these vectors are elements of a unitary unit length vector. So this is how you decompose single unitary operator, and you just plug it in here. And you do it for both gamma L0 and gamma L1. So this is what you get. And each such operation here, or each operation that we've decomposed this linear combination into, can be written like that. It is related to something called the Gibbons rotations. So it's a product of 2n minus 1 operations, or small rotations, let's say, which depend on the type, so 0 or 1, depend on the eigenvalue on this L index, and they depend on some angles, and these angles are calculated directly from these vectors. So these operations are just exponents of some Majorana operators that can hop. They allow to hop and create these linear superpositions. So like, imagine that you have the right-hand side and you would like to produce the left-hand side. So one way is to do an ansatz, that your right-hand side is a product of such simple exponents. And you might use this expansion for the exponents, which terminates at the first term exactly, and do it analytically. So like unfold it with exact equality. So this Gibbons rotation can be decomposed into a Clifford operation and RZ rotation. You can always do that. Like, you see, there are a couple of things that stack up here. We need to know how the Majorana operators are mapped onto qubits, and this is what we've showed before. Yeah, this is what we showed before. This is it. And now you have to plug it in and do a decomposition into an exponent and two Cliffords. So this is what we did. And we also proposed a coupling scheme, like you need to know which indices you want to put here in order to generate this linear combination. And for spin-dependent problems, it's by no means immediate, but if you think about it more, you might come up with a coupling like that these guys must enter these exponents and they are followed by these guys, and by these guys, etc. The common thing is that the end of one string must be exactly equivalent to the beginning of the second end. But this is maybe less relevant here. So to wrap up, we've got our gamma, and the gamma is decomposable into such a product. Such a product consists of a product of Gibbons rotations, and these Gibbons rotations can be decomposed into Clifford and arbitrary RZ rotation about some angle, which depends on the vector VLP sigma. Okay, how to write this? How much time do I have? Okay, how to write this as a quantum circuit? So bring back this guy here. Clifford, RZ rotation Clifford. And it's going to be controlled on this index L because it's a part of select. Yeah. So I wrote it this way. Sorry for mixed notation and low resolution. But this is a Clifford that has been shown previously. This is uncomputed Clifford, and there's controlled rotation. And you have a sequence of those going down to all the spin orbitals. So this is this controlled part of this, essentially. And how do you do the controlled rotations on a fault-tolerant quantum computer? How do you do controlled single qubit RZ rotations? Well, in order to perform such a multi-controlled rotation, you need to use something called the quantum dictionary, or some people call it data access oracles, or quantum RAM or QRAM. I don't know which one is better or accurate, but the point is that you have to load the angle that you want to rotate about into a quantum computer. And it turns out this is the dominant cost of your computation on a quantum computer, this little bastard here. So I'm going to spend 2 minutes describing these. But to set the stage, like get some feeling what we are doing, we want to encode some angles that are here or here on a quantum computer. And these angles got two indices, LK, like here, LK, and L corresponded to its eigenvalue, and K corresponds to the position here in this register. And each angle has some representation in binary, right? So it's got some precision, and it's indexed by B. So it's a bit representing this theta. So we assume we've got beta bits. We've got M values for L and 2n-1 values for K, as here. This is 2n-1 fixed rigid register. So we've got such a cube. So we want to load this data on a quantum computer using quantum dictionary. So how you do it? Quantum dictionaries, or let's use it data access oracles, because I'm not sure if it's the right phrase in quantum dictionaries. They work this way. You have your data access oracle. You act on an argument state, and you've got two more states here. And what's the result of it is argument state remains the same. There's a zero state here, which this is an ancilla state, but bear with me. And this D of J is our encoded information. And there's something called G of J, which is some trash we don't care about. So this is a specific implementation of this quantum data oracle, that given an argument and a function, you have the value of the function and some leftovers that you don't care about, and the argument left alone. And this D in this so-called select swap method by Wang Lo et al. It's decomposed into two main pieces. The first piece is UP, which is called the select operation in data oracle. And this select operation basically selects. So the normal way you would basically do this select operation on every argument that you have. So you would just run over all possible values for j and do a x or bit flip on every register that you want it to be bit flipped, and that's how you encode in binary your information. But what Law does, he extends the number of registers lambda times to lambda copies of it, and performs such a procedure on lambda n over lambda registers. So it might be easier to look at it when you see the circuit. So this operation here, US, is basically this part. So what you do, you have some control on Q. Q is basically part of J. It's an integer part of division by lambda. And given Q is 0, perform some bit flip operations. Given Q is 1, perform different bit flip operations. And whether you do the bit flip or not depends on the so-called bit flip matrix. And that's how I call this, probably it's differently called. But it tells you which bit should be flipped in order to encode a number. So here B is the binary representation of a number. So this is a multi-controlled knot, the most expensive part of the circuit. And there's also controlled multi-knot, which is called the quantum fan-out. And quantum fan-outs are cheap for you to get the idea, a relative idea. So this is this US part. There's also UP method called the swap, where you control on the reminders of division by lambda. So you take the reminders of the division of j by lambda. So R is just j modulo lambda. So R runs from 0 to lambda minus 1. And you swap the indices or the qubits here such that you know that the end of your circuit, your encoded data, so what you want to encode, so DJ is at qubit number 1, let's say. So this is a bit of an, you might think of an overkill, but to load data in a quantum computer. But there are benefits of that, and we adopted this method. So just for you, the quantum fan-out, so this part here, this can be done in logarithmic depth. So it's not a big issue. That's some circuit to support my claim. So to wrap up what quantum dictionary do, let's count the resources. So we've got the quantum dictionary, and we want to calculate the T count of it. I won't bother with this too much, but upon choosing proper lambda, so proper number of these qubit register copies, you might load your data of size n and precision beta on a quantum computer at the cost of square root of n beta, which is quite favorable, but it comes at the cost of extending the qubit registers to the square root of n beta. So the quantum volume sort of stays the same. So we used this so this is the only ingredient that we need to block encode our Hamiltonian. If you come back, this is the part of select, and I'm putting aside state preparation, but select requires these oracles, and these oracles effectively encode the controlled rotations, and we know the Cliffords. And these guys here are also controlled rotations about fixed angles. They're also quite expensive, but there's not much you can do about this. So having this walked through, you say that the spin orbit Hamiltonian, or the Pauli-Breit Hamiltonian, in a very naive implementation, like that you have a joint index for all spin orbitals, costs square root of 2n times beta. The QROM in the select is of this order in terms of T-gates. There are these single qubit rotations about fixed angles I've talked about. It's 4n beta. And there is some relative weight of these two circuits, and there's some extra thing. So it's still hard to assess how many gates we need if we don't run it on a particular example or molecule. But the rule of thumb is that our resource estimator, the code, says that the QROM part takes about 65% of the entire T count of the circuit, of block encoding circuit, or even the QPE circuit. Yeah, the whole QPE circuit. Right. So I'm moving to the last part, actually. So this is what would happen if you took the Pauli-Breit Hamiltonian, the double factorization method, and just used all new known techniques. Not very exciting. And in order to do something a little bit more exciting, I thought that we might come back to this form of the one-body operator. As you remember, H1 is a sum over Cartesian components, Pauli matrices, and these excitation operators, so A, dagger, A. In the Majorana representation, they look like that. So this is equal. Just switched representations. Still, this P stays here. Alternatively, you might replace these products of gammas with, as we did before, with capital gamma. And on the right-hand side, we've got these handouts that say, now our gamma operator depends also on mu, so on this component. We sort of extended our register by fourfold. But we follow a similar procedure than before. So we fold this sum into a product. And this is what we have. So now we've got two indices, L and mu, and sigma and rho for spins. And again, you might do the Givens rotation decomposition to these U's, decompose these into arbitrary rotations about Z and Clifford gates. So if you did that, you would get a block encoding circuit of this type. So you would have to produce a superposition over these FL coefficients, square roots of those, a superposition over the P sigma rho mu coefficients, and to select on all the indices that appear here and gamma. So what I'm proposing is to remove the spin control from the general select and move it aside and decouple the spin controlled operations from the orbital controlled operations. So this is a slightly schematic, not totally accurate picture, this right-hand side. So how do we do it? In two steps. The first step, the state preparation. I want to show you how to prepare states that have coefficients that are square roots of the elements of the Pauli matrices, because this is exactly the UP operation. This hasn't been done. So how you do it? You want to generate such a state. You've got 2 qubits for the spin values, so the elements of the Pauli matrix. If you think about this, there are 4 possibilities. So and there are 4 elements to or 4 positions to the Pauli matrix. And there's mu, and mu runs from 0 to 3, which is 4 numbers. You need 2 qubits, and here's the circuit. So the 2 top wires they correspond to this mu, and this is an equal superposition in mu, so you introduce Hadamard. You do control on all possible values of these mu's, because this is here, yeah. So if it's mu 0, it means the 0th Pauli matrix, which is identity. And you implement these Pauli matrices on 2 qubits, which correspond to that. And here are explicit circuits for these P0, P1, P2, P3. This is a bell pair, and there are some modifications of that. Very simple circuits. Having prepared state, so we done this. There are techniques for state preparation of that, but there's no tricks. It's just standard. So having done that, we have to show how to do this, how to decouple these orbital indices from the spin indices. And the way it's done, I mean, this is basically the highlight. You replace these multi-controlled operations with a set of operations that are controlled on single variable spin, and they are sandwiched in between these W operators. So like you recall, it's a bit involving. I'm sorry for that, but there's a lot of symbols here. But if you think about gamma LU sub sigma rho, and you decompose it into these W's, you might say that this operation here generates W sigma rho, and that's basically the point. So controlled S plus, controlled S minus from the right hand side, and W0 0, so spin independent, generates W LU sigma rho, and you do the same for the other one. So this is exactly what we want to do. So we want to map WLU00 into WLU sigma rho, and we want to do it through some unitary operations, S plus and S minus, because this is W. And this boils down to putting your hands into the Givens rotations and mapping these Givens rotations that are spin independent into something that's spin dependent. And the way it's done, so I won't bug you with that too much. I mean, this is a very similar structure, but the way it's done, you basically do a controlled swap networks. So these S operations, which decouple the spin or generate different spin components, they are just products of swap operations on certain qubits. Here I adopted the standard spin major encoding. So it's a network of swaps between the registers. If it's spin 1, if it's index 0, you do nothing. So this is essentially it. And you might summarize it in these terms, essentially. And these swaps, so these controlled swaps here that I introduced are cheap. So they can be implemented in O of 1 T-depth with no ancilla qubits. And if you look into the appendix of the work of Guang Lo, it's described there. So it's something known. So to summarize, had we implemented this one-body spin-dependent part of the Pauli-Breit Hamiltonian in a naive way, like directly, we would have to do something like this, that you have control on all the indices and component 0, 0, 0, 1, 1, 0, 1, 1. Now you move these spin indices away, and you need to only encode in select this W00 or gamma 00, to be clear. So, and these operations, the sandwich operations, are cheap. So this suggests that you might expect some fourfold reduction in cost if you were very naive. But if you use the techniques that Burke used, they showed how to swap the indices 0, 0 into 1, 1. So you basically show how to do 0, 0 into 0, 1 transition, which is sort of a 2x improvement in this particular part. as if you didn't do nothing, or you did a naive approach. And one information here is that the select circuit, so this circuit, is quite relevant because it takes about 85 to 90% of the entire T count of all QP. So it almost translates directly. This improvement here translates directly into improvement of the overall algorithm cost. With this, I'll probably finish. I won't show you, unfortunately, the exact numbers. They are still sort of under scrutiny and classified, but this might happen soon. And to conclude, we demonstrated for the first time a procedure for block encoding the Pauli-Breit Hamiltonian on a quantum computer. We use tensor network techniques and the Majorana representation to calculate the energy levels using quantum phase estimation for a general Hamiltonian. And we presented some new circuits for spin-dependent Hamiltonians. And we showed that resources that are required to calculate the ground state of the Pauli-Breit Hamiltonian are smaller, up to maybe 2 times with the use of our techniques, that if we use it, some techniques that are known in the literature directly without any thinking, which is by no means a claim of 2x, but it's just a claim that there's some improvement over a no-brainer approach if we just throw existing techniques without thinking. Further research directions, we would like to go to excited states, because this is what you care about after all, right? So intersystem crossing chemistry happens high up, or at least when you excite something. So we would like to use some filter functions. You can extend it to arbitrary total spin using Wigner-Eckhart theorem and irreducible spherical tensor formalism. And we also work on improving this quantum data access oracles. Especially, I point your attention to a new paper by Akash Nagy, a member of our Canadian team, about novel constructions for oracles. Here's Akash. And with this, I'd like to thank wonderful team members, Konrad Deka, Jan Tułowiecki, Adam Duży, and Witold Jarnicki for the mathematical scrutiny and kind support. I've received a lot of scrutiny from VTech and Konrad, and computer support from Adam, and some derivation support from Jan. So thank you, guys. This has been funded by an European Innovation Council acceleration grant that we're currently running. And as a final thought, I'd like to say that we are hiring both in Poland and in Canada. And with that, I'd like to thank you for staying with me and for your attention. Open for questions.
Great, thank you. Thank you, Emil, for a great presentation. And yes, we have some new questions on our chat. So why the second expression of Majorana representation has -i? Besides, why Hermitian?
I'm trying to locate the question first, because it's...
It was already asked just after the break.
Almost. Okay.
Why the second expression of
Majorana? There it is. Okay, yeah, that's a good question. I'll scroll back. It's very informative. Here we are. Why is it Hermitian? Why is it -i? Well, because we want to make it Hermitian. So here, this bit, I presume. So what is hermiticity? So if you do a Hermitian conjugate on that, you basically do complex conjugate on that, and you put here your dagger and no dagger here. So the sign changes, but the sign also changed by complex conjugation. That means that it remains unchanged by the Hermitian conjugate, hence -i.
Okay.
And
good. All right. Next question. This might be in your references, but can you recommend any background on this factorization from a mathematical point of view, given that the physics constrains certain operators to be Hermitian and Pauli matrix factors?
Oh, I just have an open paper which does a nice overview of tensor network techniques. I just stumbled upon it yesterday, so might be nice to look at. This paper is quite informative, educational in a way. But there's a lot of literature on tensor network approaches, and I don't know. I'm not an expert in this by no means, but if you look into von Berg et al. Physical review research, so this paper, this method is outlined there quite nicely, and there are further references therein. So it might be the quickest way.
Okay, good. All right, another question. On slide 48, why for SM sigma is lower than rho?
Oh, that's a good question again. Well, so it's a special case. So if you had it's just so it's a special case. Normally you would have two more cases when sigma is equal to rho and sigma is greater than rho. I didn't want to flood you with too many lines of equations. Probably there's a way of folding it into one somehow. But in spin major, sigma smaller than rho basically means that sigma is equal to -1/2 and rho is +1/2, or sigma is alpha and rho is beta. So we know that this suggests that the spin 1 guys are on the right here, and the spin 0 guys are on the left here. And if you switched it, yeah, I'm not sure if maybe you probably didn't get exactly the same form here. You'd have to swap some indices. So this is just a special case. This is a short answer, and just for demonstration purposes. So in our paper that we about to submit soon, you'll probably find full case for spins.
All right.
So it's no restriction here on spins.
Okay, there's another question. I'm not sure to which slide it concerns, but why NC is equal to SM minus OM?
Oh, right. So what I wanted to show here is how many non-identity gates you have in this expression when you use the spin major encoding versus when you use the orbital major encoding. Hence, I calculate the weight, so the number of non-identity Clifford gates for spin major encoding, so like in here, basically, not just for one spin. And then I do the same for orbital major encoded, not shown, but very similar, and take the difference, numeric difference, the count, and this is what I get. And it tells you that the orbital major, so like if this is big, it means that the spin major encoding has a lot more non-identity gates than the orbital. So it's worse. We want to have as few gates as possible. So it's just a snippet of estimate.
Okay, good. Then on slide 50, could you explain a bit on unitary folding transformation?
Right. So the first observation is, like, look at this equation, and we know that gamma p sigma x, as we just discussed, is Hermitian, It's self-inverse because it's unitary. So if you take a square of it, you get identity. And if you these V's, subscript L and superscript L and subscript P sigma, they are elements of a unit vector. L labels columns in some unitary matrix, and P sigma labels rows. So if you pick a column, your vector has unit length and is orthogonal to all other vectors. And so essentially, you can do an ansatz or think of a transformation that will subsequently generate this sum term by term. And this is, let's say, necessary condition that this operator is Hermitian and self-inverse, because if you think about this ansatz here with exponent, if it wasn't, you would get infinite expansion, or expansion that's more than one term beyond identity. So like every term that's quadratic will probably die off. Yeah. So this property of Majorana matrix operators is crucial for this to be possible. And you might try to do an ansatz and just guess that this product will generate it. And you might, if you do this ansatz, you have to relate these angles to these components. And there's a simple relation. It's a hierarchical set of trigonometric equations, which is simple to solve, like arc sine, arc cosine. So there's a direct mapping. Vitek, my colleague, pointed out that this is just a point on a n sphere, and you do the mapping between n spheres here. So if you inspect it carefully and use these properties, you can do it. It comes out naturally, but you have to pick these indices carefully.
Mm-hmm.
A bit of a design of an algorithm.
Good. There's another question. From which paper could you obtain the Q-ROM big O complexity expression on slide 58?
Mm-hmm. Here. So this is from the paper of Guang. It's a wonderful milestone paper. I'll show you this is the reference here in the bottom corner. So 2018, but still active, this paper. So this is where you can find it. You'll probably find it also in our paper, in our appendix soon. And this tilde over O is just that you drop any logarithmic terms, but it's irrelevant here in this midst of many numbers. So I'm showing this again.
Okay.
Mm-hmm.
Good, thank you. And I think this is the last question. Can we get the slides?
No.
No.
Not yet.
Okay.
Mm-hmm. In a couple of weeks, I'll be very, very happy to share the slides.
Mm-hmm. Okay.
I think there's one more question on slide 69. Any reason for the specific use of different rotation?
Okay.
Yes.
69 or possibly let's okay, 69. So either it's a deep question or it's the wrong slide, because if it's a deep question, then it's probably a question about, I'm trying to decipher it, because this is sort of a Givens rotation decomposed into Clifford and control Z rotation. Why is there any reason for the specific use? So it's done here in, as you can see, in the orbital major encoding. We could do it in spin major encoding. There's nothing wrong about that. And one thing that's important here is that these Cliffords depend on spin. If they depend on spin, it makes things harder later on. But you can't really remove the spin dependence, because the spin dependence stays with you from the beginning. Like this is what the Pauli-Breit Hamiltonian is all about. It depends explicitly on spin, and the spin dependence stays here. Later we show how to remove it, or like to handle it without much pain. But there's no specific reason for using this type of rotation over the other encoding or different any other type. This is how it is. Yeah.
Okay. All right. Do we have more questions, Emil? Maybe someone would like to unmute and ask. Last chance to ask. All right, I don't see more questions now. So, Emil, thank you once again for a great presentation and for answering all the questions that we had. That was quite interesting and informative lecture and discussion. And yeah, we would like to thank everyone for attending today and participating in discussions, asking very interesting questions as well. And we hope to see you next time. So just to remind, next week there will be the next meetup. So we hope to see you then, and have a good weekend, everyone.
Thanks, everyone. Thanks for coming. Thank you.